A star already moving through the Milky Way will pass closer to the Sun than almost any other known star, and if a star ever crossed straight through the solar system, its gravity could fling a planet into interstellar space. Gaia satellite tracking shows that star, catalogued as Gliese 710, will brush the outer edge of our solar system in about 1.3 million years, and it will not touch a single planet. But if a star like it, or one on a still closer path, ever crossed directly through the solar system, the same gravity that holds Earth in its yearly orbit could just as easily fling a planet into interstellar space or drown the inner solar system in a rain of comets. What follows starts from what astronomers know for certain about the space around the Sun, then follows the real physics of gravity as far as a genuinely close stellar pass would carry it. Nothing here is a prediction. It is a disciplined thought experiment about how fragile or how resilient the quiet order of the solar system actually is. The Sun is not sitting still in a fixed pocket of space. It carries the entire solar system in a long orbit around the center of the Milky Way, one full circuit taking about 230 million years, and along that path it drifts past countless other stars at distances so large that almost none of them ever tug noticeably on a single planet. Proxima Centauri, the nearest star to the Sun, sits about 4.2 light-years away, a gap so vast that light itself needs more than 4 years to cross it. Real close approaches do happen anyway, though rarely, and astronomers can now name one with real confidence. Using data from the European Space Agency's Gaia satellite, which has measured the position and motion of more than 1 billion stars, with a precision that would have been unthinkable a generation ago, researchers have calculated which stars will drift closest to the Sun over the next several million years. One candidate stands out from all the rest. A star catalogued as Gliese 710, an ordinary orange dwarf star smaller and cooler than the Sun, is moving on a path that current tracking says will bring it within roughly a light-year of the Sun in about 1.3 million years. That is still far outside the solar system as anyone would recognize it, thousands of times farther out than Neptune's orbit. But on a galactic scale it counts as remarkably close enough to brush the outer edge of the Oort cloud, the vast frozen halo of comets thought to surround the Sun far beyond the planets. Astronomers reconstruct a path like this by combining 2 measurements for each star, its motion sideways across the sky, called proper motion, and its motion directly toward or away from the Sun, called radial velocity, read from a shift in the star's light. Gaia measured both for over 1 billion stars, turning what used to be a rough statistical guess about stellar traffic near the Sun into specific, checkable predictions for individual stars. Gliese 710 stands out precisely because its motion happens to point almost directly at the solar system, the rarest and most consequential kind of stellar path there is. This account starts from that real, tracked case and then asks a harder question. Gliese 710's actual predicted path keeps it well short of the planets themselves. But what would happen if a star, on some other trajectory that no current data confirms, passed not just near the outer edge of the solar system, but directly through it, close enough to swing past the orbits of the planets? That is not a prediction. Current models predict nothing like it is due at any specific date, and the evidence suggests such an event is astronomically rare across the roughly 4.6 billion years the solar system has existed. But rare is not impossible, and the physics of what would follow is worth tracing carefully, because it reveals something true about how the arrangement of planets around the Sun actually holds together. The scale involved is hard to hold in mind without a comparison. If the Sun were shrunk to the size of a marble sitting on a table, Proxima Centauri would be another marble roughly 1,100 kilometers away, about the distance from New York to Chicago and back again. Between those 2 marbles there would be nothing at all, no dust, no light, no other object of any kind, just a near-perfect vacuum threaded by the faint pressure of starlight. A star crossing that gap does not brush past casually. It has to travel an enormous distance on a trajectory that, by sheer chance, threads a target far smaller than the gap itself. That is the real reason such passages are rare, not because gravity is weak, but because the space between stars is so overwhelmingly empty that 2 of them seldom come close enough for gravity to matter. Whatever a hypothetical closer star's exact path, the first part of the solar system it would ever reach is not a planet at all. It is the enormous, thinly populated shell of icy debris that begins where the planets end and stretches nearly 1/4 of the way to the next star, the Oort cloud. Nothing about the Oort cloud has ever been photographed directly, No telescope has resolved a single one of its objects because they are small, dark, and unimaginably far away. Its existence is inferred instead from the long looping paths of comets that occasionally fall in toward the Sun after spending most of their existence in the outer dark. Astronomers describe the Oort cloud as a nearly spherical shell of icy bodies, mostly frozen water, ammonia, and methane left over from the same disk of gas and dust that built the planets 4.6 billion years ago. Rather than settling into flat orbits like the planets, this leftover material was scattered outward long ago by the gravity of the young giant planets, chiefly Jupiter and Saturn, and thrown into a vast, slowly rotating halo that surrounds the whole solar system. The distances involved dwarf anything in the planetary part of the solar system. Astronomers measure distances within the solar system in astronomical units, one astronomical unit being the average distance from the Earth to the Sun, about 150 million kilometers. Neptune, the outermost planet, orbits at about 30 astronomical units. The inner edge of the Oort cloud is thought to begin somewhere around 2,000 astronomical units, and its outer edge may extend to 100,000 astronomical units or more, close to 1.5 light-years from the Sun. Put another way, if the planets fit comfortably inside a room, the Oort cloud would be a thin shell of scattered ice wrapped around an entire city block. Despite containing what may be trillions of individual bodies, the Oort cloud is not a dense or crowded structure, and it is worth being precise about that because the same misconception that pictures the asteroid belt as a field of rocks close enough to dodge applies here with even more force. Individual Oort cloud objects are typically millions of kilometers apart from their nearest neighbors. A spacecraft could cross the entire cloud and never come within visual range of a single object by chance. What makes the Oort cloud significant is not density but sheer number and sheer reach. Enough icy bodies, spread across enough volume, that even a small fraction disturbed from their orbits can supply a steady trickle of comets toward the inner solar system for millions of years. The objects out there are also barely held by the Sun's gravity at all. At 50,000 astronomical units, the Sun's pull on a small icy body is thousands of times weaker than it is on Earth, weak enough that the combined gravity of the rest of the galaxy, and any star that happens to pass nearby, competes on nearly equal terms with the Sun's own hold. The planets, tucked in close and moving fast, are gravitationally stubborn. They would resist almost anything short of a star passing directly among them. The Oort cloud, drifting slowly at the outer edge of the Sun's influence, is the most fragile part of the entire solar system, the part most easily nudged by an outside visitor. Oort cloud comets that do eventually fall inward take an extraordinarily long time to arrive, their orbits stretched so far that a single trip from the outer cloud to the inner solar system and back can take millions of years. Halley's Comet, by contrast, is a short-period comet whose orbit has already been shaped by repeated close passes near the Sun and the planets, returning roughly every 76 years. It is not a native of the deep Oort cloud in its current form, though comets like it may have originated there long ago. The Oort cloud is not a fixed inventory that simply empties out. It is a slow-motion reservoir constantly reshuffled by small gravitational nudges from passing stars, from the galaxy's own tidal pull, and, if a star ever passed close enough to reach directly into it, by that encounter as well. That reach is exactly what a close stellar pass would achieve first. Long before any hypothetical star came near a single planet, it would pass through this outer shell, and the shell would respond exactly as its fragile, barely bound structure predicts. Gravity does not switch on and off at some fixed boundary. It simply weakens with distance, following an inverse square rule that astronomers can calculate precisely for any two masses at any separation. That means a passing star does not need to enter the solar system to affect it. Even while still light years away, its gravity reaches into the Oort cloud and begins tugging on the loosely bound ice out there, adding its pull to the Sun's own already weak grip. In this scenario, the closer the star's path brought it and the greater its mass, the stronger the added tug would be, and the more of the Oort cloud's population would have its orbit measurably bent. Computer models built by planetary scientists suggest that a star passing within roughly 1 to 2 light-years of the Sun, on the close end of what Gliese 710 is expected to do, would likely perturb only a modest fraction of Oort cloud objects, enough to nudge the long-term comet supply rate, but not enough to be dramatic on human timescales. A star passing much closer, within a few thousand astronomical units, deep inside the Oort cloud itself, would be a different matter entirely. Models of such an encounter suggest the intruding star's gravity could scramble the orbits of a significant share of the Oort cloud's inner population, some objects flung outward into interstellar space forever, and others knocked onto new paths that dive back toward the Sun. The timescale for this to unfold is itself worth grounding. A star passing at even a modest fraction of typical stellar speeds, on the order of 20 to 100 kilometers per second, would not linger near the Oort cloud for long in absolute terms, crossing the entire outer solar system in a matter of a few tens of thousands of years. But the orbital periods of the objects it disturbs are so long, often measured in millions of years, that the effects of even a brief gravitational encounter would continue unfolding for ages after the star itself had moved on, the way a single stone dropped in a very large, very still pond keeps sending out ripples long after the splash. What actually happens to a disturbed Oort cloud object depends on the specific geometry of its encounter with the passing star, something that current models can only describe statistically rather than object by object. Some icy bodies would have their orbits stretched into longer, more elongated shapes without changing their general distance from the Sun. Others would be nudged onto paths that carry them, for the first time in the age of the solar system, close enough to the Sun and the planets to eventually become visible as comets. Still others, on the unluckiest trajectories, would gain enough energy from the encounter to be ejected from the Sun's gravity altogether, becoming permanently interstellar wanderers, unbound from any star at all. Astronomers already suspect that many, and perhaps most, of the small icy and rocky bodies drifting freely between stars started out exactly this way, ejected from someone else's Oort cloud by an ancient stellar encounter of their own. None of this would be visible from Earth as it happened. A gravitational nudge to a comet a light year away produces no light, no sound, and no immediate change to anything a person could observe. The evidence would arrive later, gradually, as a rise in the rate of new comets entering the inner solar system over the following hundreds of thousands to millions of years, a subtle statistical shift rather than a single dramatic event. In this scenario, the true legacy of a close stellar pass would not be the pass itself. It would be everything the pass set loose afterward, falling inward one comet at a time, long after the star that caused it had receded back into the galaxy. That falling inward, and what it would eventually mean for the inner solar system and for Earth, is the part of this thought experiment with the most concrete physical stakes. A comet is, at its simplest, a chunk of ice and rock that has fallen close enough to the Sun for sunlight to warm its surface and boil some of that ice directly into gas, a process called sublimation. That escaping gas and dust, pushed outward by sunlight and the solar wind, forms the glowing tail that makes a comet visible from Earth, sometimes for weeks at a time. Most comets people see today are old, familiar visitors on well-mapped orbits, discovered decades or centuries ago and tracked ever since. In this hypothetical scenario, a disturbed Oort cloud would eventually begin sending something rarer, a steady increase in comets never seen before, arriving on long unfamiliar orbits shaped by an encounter that happened long before any human civilization existed to notice it. The increase would not be instantaneous, and it would likely not be even. Because Oort cloud orbits are so enormously long, the newly disturbed comets would arrive over a stretched-out span of time, some reaching the inner solar system within tens of thousands of years of the stellar encounter, others taking 1,000,000 years or more to complete their long fall inward. Current models suggest the rate of new comets could rise well above its normal background level for a substantial stretch of that period, then gradually taper back down as the disturbed population thinned out. A civilization living through the peak of such a period might notice, over the span of many human lifetimes, that comets seem to be appearing more often than the historical average, without any single event marking the change. An increase in the comet supply is not by itself a catastrophe. Long-period comets, even at an elevated rate, would still be rare individually, and the overwhelming majority would pass through the inner solar system without coming anywhere near Earth, following orbits shaped mostly by the Sun's own gravity and only nudged by the ancient stellar encounter. The real consequence would be statistical rather than singular. More comets in total means a larger population from which, purely by chance, an unlucky one could eventually cross Earth's orbit at the wrong moment. Astronomers who study impact risk describe this exact mechanism, sometimes attributed to past stellar encounters, as one plausible contributor to long-term variation in the rate of comet impacts across Earth's geological history, though the evidence linking any specific past impact to any specific stellar flyby remains difficult to establish with confidence. It is worth being precise about what this scenario does and does not claim. It does not say that a passing star would aim a comet at Earth. Comets disturbed from the Oort cloud follow ordinary orbital mechanics, shaped by the Sun's gravity and the accumulated gravity of the planets, with no preference for any particular target. What a close stellar pass would do in this hypothetical is raise the total number of comets in play over a long stretch of time, which raises the odds, without guaranteeing any specific outcome, the way rolling a single die many more times raises the odds of eventually rolling a 6, without making any one roll more likely to be that 6. Earth itself carries physical evidence that comet and asteroid impacts have shaped its history before, most famously the impact 66 million years ago that is widely understood to have ended the age of large dinosaurs, though that particular object is generally thought to have been an asteroid rather than a long-period comet. The broader geological record shows that impacts of various sizes have struck Earth repeatedly across its history, at a rate that itself appears to vary over long timescales in ways not fully explained by chance alone. Whether past stellar encounters, including undiscovered ones the fossil record cannot resolve, contributed to some of that variation remains an open question that current evidence cannot settle either way. Whatever a disturbed Oort cloud eventually sent inward, it would represent only the earliest and gentlest stage of what a genuinely close stellar pass could do. A star that stayed at Oort cloud distance would never come near enough to threaten a planet directly. The physics changes entirely once a star's path is imagined crossing much closer into the region the planets themselves occupy, and before reaching that extreme case, it helps to look at the one time in Earth's recent history that a star actually did pass unusually close, without anything like this scenario occurring. In 2015, astronomers analysing the motion of a faint red dwarf star, formerly catalogued but commonly known as Shoal's star, calculated that it had almost certainly passed extremely close to the Sun in the astronomically recent past, an event dated to roughly 70,000 years ago, well within the span of modern human existence. Their reconstruction placed the star's closest approach at somewhere around 50,000 astronomical units from the Sun, deep inside the outer Oort cloud, though still enormously far beyond any planet. Shoal's star is a small, dim red dwarf, part of a pair orbiting a slightly larger companion, together carrying only a modest fraction of the Sun's mass. That low mass matters enormously to how much damage its passage could have done. The strength of a gravitational disturbance depends both on distance and on mass, and a star this light, even passing this close, would exert only a fraction of the gravitational pull that a Sun-sized or larger star would at the same distance. Researchers modelling the encounter concluded it likely did nudge some Oort cloud objects onto new orbits, the same kind of gravitational tug that governs any object loosely bound at that distance, but found no clear evidence tying it to any specific spike in comet impacts or extinction events on Earth around that time. The case of Shoal's star is valuable precisely because it is not hypothetical. It shows that close stellar passages, at least at Oort cloud distances, are not purely theoretical exercises confined to computer models. They happen on real, checkable timescales, close enough to living memory in geological terms that scientists were able to reconstruct one after the fact, using the star's own present-day motion, essentially running its trajectory backward through time like rewinding a film. It also demonstrates something reassuring about scale. A close pass by a small, dim star at Oort cloud distance appears to have left no discernible mark on Earth or its history. Gravity this far out, from a star this modest, producing effects too gradual and too diffuse to register as any single dramatic event. Not every stellar encounter in the Sun's history would have been this gentle, and researchers have used the same backward tracing technique on other stars to identify additional past and future close approaches. Most fall in the same broad category as Shoal's star and Gliese 710, real, tracked and confined to Oort cloud distances or farther, never approaching the planets. None identified so far comes remotely close to entering the region where the planets themselves orbit. That absence is itself informative. If a star has crossed directly through the planetary part of the solar system at any point in the last several 100,000 years, current data has found no trace of it, and no candidate star's reconstructed path suggests it. Shoal's star matters here because it anchors what comes next in something concrete. The question ahead is not whether physics might behave in some exotic, unprecedented way. It is what would happen if a star did what stars occasionally, verifiably do, only closer, on a path bold enough to cross not just the Oort cloud but the Kuiper belt and the orbits of the planets themselves. Scholl's star confirms that a star reaching into the Oort cloud is not speculation, it is confirmed history. What lies closer in, and more consequential, moves past confirmed history into careful extrapolation. To trace those closer stages honestly, the next step is to establish exactly what stands between the Oort cloud and the planets, because a star crossing that gap would encounter a second, very different population of icy and rocky bodies, long before it ever reached anything resembling a world. Between the Oort cloud, where Scholl's star and Gliese 710 make their real and hypothetical closest approaches, and the orbits of the planets, lies an enormous stretch of space that is, for the purposes of this scenario, essentially empty. A star on a path aimed at the inner solar system would spend the overwhelming majority of its transit crossing this gap, tens of thousands of astronomical units of near-total vacuum, before its gravity became strong enough to do anything more dramatic than the slow Oort cloud disturbance already traced. This is the part of the scenario where the sheer scale of the solar system does most of the protective work, simply by being so large that almost any plausible stellar path passes through mostly nothing before it reaches anything. If such a star did stay on a genuinely direct course, its gravitational influence would grow steadily stronger as the distance closed, following the same inverse square relationship that governed its effect on the Oort cloud, only now compressed into a much shorter final stretch. A star still 1,000 astronomical units away exerts a pull on the outer solar system, many times weaker than the same star at 100 astronomical units, and many thousands of times weaker again than at 10 astronomical units, close to Saturn's own distance from the Sun. This means the most dramatic effects of any such passage, in this hypothetical, would be compressed into a relatively brief final stage of the encounter, likely lasting from a few centuries to a few thousand years depending on the star's speed, sandwiched between very long, very gentle approach and departure phases. The star's own mass would also matter more with every step closer. Scholl's star's low mass helps explain why its real confirmed passage through the outer Oort cloud left so little trace. A star with roughly the Sun's own mass, or a more massive star still, following a comparably close path, would exert a substantially stronger pull at every distance along the way. For that reason, this account treats the intruding star as a modest one, broadly sun-like or somewhat smaller, rather than reaching for an unusually massive star, merely to make the scenario more dramatic. A heavier star would only intensify every consequence described here, not change its basic shape. Speed matters as much as mass. A star moving unusually fast relative to the Sun would spend less total time within any given distance, limiting how long its gravity had to act on any one object, while a star moving unusually slowly would linger and could, in principle, do more cumulative damage even at a similar closest distance. Typical relative speeds between stars near the Sun run from roughly 20 to a little over 100 kilometers per second. This account assumes a speed in the middle of that range, fast enough that the entire encounter, from the edge of meaningful gravitational influence to departure, would likely play out over a span measured in centuries to a few thousand years, not longer. What this closer approach would first encounter before reaching any planet is a second reservoir of small icy and rocky bodies far less remote than the Oort cloud, but still well beyond Neptune, the Kuiper belt, home to Pluto and thousands of other known smaller worlds. Unlike the Oort cloud, the Kuiper belt is close enough and well enough mapped that astronomers can describe with real confidence what a disturbance there would look like. Because, unlike the Oort cloud's hypothetical population, much of the Kuiper belt's real population has already been directly observed. The Kuiper belt is a disc-shaped region of icy bodies beginning just beyond Neptune's orbit, at about 30 astronomical units from the Sun, and extending out to roughly 50 astronomical units well inside the distances where the Oort cloud begins. Unlike the Oort cloud, the Kuiper belt is not merely inferred. Thousands of its larger members have been directly observed and catalogued by telescopes, including the dwarf planet Pluto, its large moon Charon, and other significant bodies such as Eris and Sedna, the last of which already follows an unusually elongated orbit that some researchers suspect was itself shaped by a past gravitational disturbance, possibly from a passing star or an undiscovered distant planet. A star passing through this region, in this hypothetical scenario, would find a population of icy worlds occupying orbits that are, on average, less tightly bound than the planets closer to the Sun but considerably more tightly bound than anything in the Oort cloud. Kuiper belt objects orbit the Sun on timescales of centuries, not the millions of years typical of the outer Oort cloud, meaning a gravitational disturbance here would produce visible consequences on a comparatively human timescale, rather than unfolding across geological ages. A sufficiently close stellar pass could scatter a meaningful fraction of Kuiper belt objects onto new, more eccentric orbits, some flung outward to join the Oort cloud or leave the solar system entirely, others perturbed onto paths that would carry them inward, past Neptune, and eventually into the realm of the giant planets. Something like this is believed to have happened before in the solar system's own history, though not because of a passing star. During a period roughly 4 billion years ago, sometimes called the Late Heavy Bombardment, researchers studying the orbits of the outer planets have proposed that a shift in the positions of Jupiter, Saturn, Uranus, and Neptune themselves, rather than any visiting star, scattered a large portion of what was then a much denser Kuiper belt, sending a wave of icy and rocky debris throughout the solar system and cratering the Moon and the inner planets over a span of hundreds of millions of years. That episode shows the underlying mechanism. A disturbance scattering the outer solar system's small bodies inward is not exotic. The solar system has plausibly already lived through something like it, driven that time by the planet's own gravity, rather than a stellar intruder. A star passing through in this hypothetical would add an outside gravitational actor to a system that, in the late heavy bombardment, disturbed itself. The Kuiper belt's response would likely follow a similar broad pattern. Some objects flung entirely out of the solar system, some scattered into new stable or semi-stable orbits farther out, and some sent inward on paths that would eventually cross the orbits of Neptune and Uranus. None of this would happen instantly. Even at Kuiper belt distances, orbital periods run from roughly 90 years for the innermost objects to several centuries for those farther out. So a disturbance here would still take decades to centuries to fully play out, a slow unravelling rather than a single moment of chaos. What makes the Kuiper belt significant here is not that it holds more mass than the planets. It holds a small fraction of Earth's mass in total, spread across thousands of individual bodies. What matters is proximity. A star that has reached the Kuiper belt has crossed almost the entire distance separating interstellar space from the planets themselves, and the same gravity that scatters icy dwarf worlds here would, on a sufficiently close path, reach the orbits of Neptune, Uranus, Saturn, Jupiter, and eventually the inner rocky planets, including Earth. That is the point where the scenario stops disturbing debris and starts disturbing worlds. A planet stays in a stable orbit because two forces are in a long-running balance. The Sun's gravity constantly pulling it inward, and the planet's own sideways motion constantly carrying it forward so that it falls toward the Sun and misses forever. This balance is remarkably durable against small disturbances. The planets have held their current basic orbits for roughly 4.6 billion years, weathering countless minor tugs from each other and from Jupiter's dominant gravity. It is far less durable against a large, close, unfamiliar mass suddenly entering that balance, because a passing star does not participate in the balance at all. It simply adds its own competing pull, and orbits respond to competing pulls by becoming unpredictable. Orbital dynamicists, scientists who study how gravitating bodies move under each other's influence, describe systems with three or more massive bodies interacting as chaotic in a precise mathematical sense. Even tiny differences in starting conditions lead to wildly different outcomes over time, and no simple equation can predict the final result, the way a single planet orbiting a single star can be predicted with near-perfect precision. Introducing an entire additional star into the solar system, even briefly, turns the 8-planet solar system into exactly this kind of unpredictable many-body problem for as long as the visiting star's gravity remains significant. Researchers running computer simulations of hypothetical stellar flybys through model planetary systems consistently find that even a single, relatively brief encounter can permanently alter the shapes of the planet's orbits, stretching some into longer ellipses, tilting others out of their original plane, and in some simulated cases ejecting a planet from the system altogether. Which planets would be affected most, and how severely, depends heavily on exactly how close the passing star's path came to each one, something no version of this thought experiment can specify without inventing a level of precision the scenario does not actually have. What the simulations do show consistently is a rough pattern. Planets farther from the Sun, moving more slowly and more loosely bound by the Sun's gravity, are generally more vulnerable to being disturbed or ejected by a passing star than planets close in, which move faster and are more tightly held. That would put Neptune, Uranus, and to some extent Saturn at greater risk in this scenario than Jupiter, and would put Jupiter at greater risk than the 4 smaller rocky planets closest to the Sun, including Earth, which are the most tightly bound of all. This does not mean Earth would necessarily emerge from such an encounter unaffected. Even without a direct close pass, changes to the orbits of the giant planets, particularly Jupiter and Saturn, would themselves ripple inward because their gravity already exerts a small but real influence on the orbits of the inner planets today, an influence that keeps the whole system in a long-term, gently oscillating balance. Disrupting that balance at the outer edge could, over subsequent centuries, subtly alter the shape of Earth's own orbit, or its tilt relative to the Sun, changes that would likely be small compared to what a direct hit on the outer planets would cause, but not necessarily negligible, and not something current models can rule out with total confidence for every possible version of this hypothetical encounter. A disturbed Oort cloud comet or a scattered Kuiper belt object represents a loss of a small icy body from a population of trillions or thousands. The solar system as a whole barely notices. A planet's orbit, once meaningfully bent out of shape by a passing star, does not spring back afterward. There is no mechanism inside the solar system strong enough to undo it. Whatever new orbit a planet settled into after such an encounter, whether slightly altered or catastrophically so, would very likely be its orbit from then on, for as long as the solar system continued to exist. The most extreme version of that permanence, a planet gaining enough energy from the encounter to leave the solar system altogether, deserves its own careful treatment, because the physics behind it is the same physics that lets spacecraft use planets themselves to gain speed for real interplanetary missions today. Space agencies have used a well-understood gravitational trick for decades to send spacecraft to the outer solar system without carrying enough fuel to get there directly. Spacecraft flying close past a planet on the correct approach angle can borrow a small amount of the planet's own orbital energy, leaving the flyby measurably faster than it arrived, while the planet itself loses an amount of energy too small to ever detect, because the planet is so enormously more massive than the spacecraft. NASA's Voyager missions used exactly this technique, called a gravity assist, at Jupiter and Saturn to reach the far outer solar system decades earlier than a direct trajectory would have allowed. The same physics runs in the other direction when the masses involved are closer to comparable, and a passing star, unlike a spacecraft, is not a negligible mass compared to a planet. Even a small star carries hundreds of thousands of times the mass of Earth, and can be a meaningful fraction of the Sun's own mass. In this hypothetical scenario, a planet passing close enough to such a star, on the right geometry, could gain a significant fraction of the star's own orbital energy in a single encounter, the same mechanism as a spacecraft's gravity assist, only scaled up enormously and running toward the planet instead of away from it. If that energy gain were large enough, the planet's own velocity relative to the Sun could exceed what is called escape velocity, the speed above which an object's path curves away rather than falling back, and the planet would leave the solar system permanently, continuing forward into interstellar space on its own, no longer orbiting anything. This is not a fringe idea invented for this account. Researchers studying planetary systems around other stars have found strong indirect evidence that this exact process happens elsewhere in the galaxy. Astronomers have identified what are called free-floating planets, worlds with no host star at all, drifting alone through interstellar space, detected through subtle gravitational effects on background starlight. Current models estimate that free-floating planets may be common across the galaxy, and ejection by a close stellar encounter, along with ejection by a system's own internal gravitational instability, is considered one of the leading explanations for how they came to be alone. If this process happens often enough elsewhere to leave a detectable population of orphaned worlds, then in this hypothetical scenario, it would be physically plausible for a sufficiently close, sufficiently fast stellar encounter to do the same thing to one of the Sun's own planets, most likely one of the outer, more loosely bound giants rather than one of the rocky inner worlds. An ejected planet would not explode, break apart, or experience anything especially dramatic at the moment of ejection itself. From the planet's own perspective, It would simply be moving on a hyperbolic trajectory rather than an elliptical one, the same smooth curve followed a moment before, just no longer closed. What would change, gradually and then completely, is everything downstream of receiving the sun's light and warmth. A planet like Neptune, already extremely cold and largely dependent on its own internal heat rather than sunlight, might change less dramatically in the short term than a warmer inner world would if it somehow suffered the same fate, though any ejected planet would eventually cool far below anything it experiences while still orbiting a star, its remaining heat radiating slowly away into the near absolute zero cold of interstellar space over a span of many millions of years. For Earth specifically, direct ejection from the solar system by a stellar encounter would require an extraordinarily close and extraordinarily improbable pass, because Earth's orbit is small and fast and tightly bound compared to the outer planets. Current models treat this as one of the least likely outcomes of any plausible stellar flyby scenario, far less likely than disturbance of the outer planets or the Kuiper belt. What Earth would more plausibly experience, in almost every version of this hypothetical short of the most extreme, is not ejection but a set of subtler, still consequential physical effects, felt at the surface rather than in the shape of its orbit. It is tempting to imagine a star passing anywhere near the solar system as a second sun rising in the sky, flooding Earth with extra heat and light. The physics of brightness does not support that picture, except at the very closest of the distances this account has considered. A star's apparent brightness fades with the square of its distance from observer, the same rule that governs the sun's own light reaching the planets, and even a star with the sun's own intrinsic brightness would need to close to a genuinely small fraction of an astronomical unit, far closer than any planet's own orbit, before it delivered anything close to the sun's own warmth to Earth. At the distances relevant to a star crossing the outer planets, or even the Kuiper belt, in this hypothetical, the intruding star's light would be far too faint for a person on Earth to feel any change in temperature at all. It might, at its closest approach, become a strikingly bright point of light in the night sky, brighter than any star currently visible, and perhaps bright enough to see faintly in daylight, but not a source of meaningful heat. The more serious concern, and the one this account has already spent most of its attention on, is not direct heat or light from the star itself but the secondary effects. A planet's orbit altered, or the local rain of comets and debris increased by the star's gravity. If a genuinely close encounter, one that reached all the way into the inner solar system, altered Earth's own orbit or the tilt of its axis even slightly, the consequences for climate could be significant over subsequent centuries, since Earth's climate is sensitive to exactly these variables. Small, slow natural changes in Earth's orbital shape and axial tilt, known as Milankovitch cycles, are already understood to drive the multi-thousand-year rhythm of ice ages across Earth's real geological history. A stellar encounter severe enough to noticeably alter these same parameters would, in this hypothetical, act like an unusually abrupt and unpredictable version of a process the planet already experiences naturally and gradually. A more immediate risk, in the scenario where the star's passage substantially increased the local rate of comets and disturbed debris, would be a modestly elevated chance of impacts on Earth over the following centuries to millennia. Not a single dramatic bombardment, but a statistically raised background rate, consistent with the mechanism traced several chapters earlier. Any individual comet or asteroid large enough to cause serious damage on impact remains. Even under an elevated rate, a rare event on human timescales, the geological record shows that impacts capable of causing global consequences on the scale of the event 66 million years ago are exceptionally infrequent even during periods when the impact rate is thought to have been elevated for other reasons. One further effect deserves mention and equally firm hedging. Some researchers have proposed that a very close stellar encounter, particularly with a compact, dense stellar remnant, could, in principle, disturb Earth's own moon or trigger unusual tidal stresses if the passing object came remarkably close, closer than almost any scenario this account has treated as plausible. Current evidence gives no reason to expect this outcome from a realistic flyby at planetary distances, and it is included here only to be complete about what the outer edge of possibility looks like, not because it is a likely part of this scenario. Taken together, the honest picture this account arrives at is that Earth's greatest physical risk from a close stellar encounter is not the star itself, but everything the star's gravity sets in motion elsewhere in the solar system. Arriving at Earth secondhand, gradually and unevenly over a span of centuries to millions of years, rather than as any single catastrophic night. The one scenario left untreated, and by far the least likely of all, is a direct collision between the Sun system and the star itself, and it deserves its own careful, heavily hedged accounting before this thought experiment can honestly conclude. A true collision, in the sense of one star's outer material physically striking another star or a planet, would require a pass so close that it falls into an entirely different category of improbability, several orders of magnitude rarer than a distant gravitational disturbance. Stars themselves are, relative to the space between them, extremely small targets. The Sun's diameter is about 1.4 million kilometers. The distance to even the nearest other star is roughly 40 trillion kilometers, meaning the Sun occupies only an infinitesimally small fraction of the space along that path. For two stars to actually collide, their paths would need to intersect almost perfectly, a geometric coincidence astronomers regard as effectively negligible in the current, relatively sparse environment around the Sun, sometimes described informally as the stellar neighborhood's low-density suburbs of the galaxy. Direct stellar collisions are understood to happen far more often in a genuinely different environment, the extremely dense cores of globular star clusters, tightly packed collections of hundreds of thousands of stars, where individual stars really can pass close enough, occasionally, for actual contact. The Sun does not live in an environment remotely like that, and current understanding of the galaxy's structure gives no indication it ever has. If, purely as a hypothetical extension of an already vanishingly unlikely scenario, two stars did collide directly, the physical outcome would depend enormously on the masses and internal structures involved, and would not resemble a simple explosion. Researchers who model these encounters, drawing on the more common case of stars merging inside dense clusters, describe a violent but comparatively slow process by stellar standards, playing out over hours to days rather than an instant, as the outer layers of each star are stripped and mixed by tidal forces before the star's cores either merge into one larger star or, in some outcomes, produce debris that is flung away rather than fully combining. Some merger events are thought to briefly and dramatically brighten the resulting star, an event astronomers call a luminous red nova, though the confirmed examples of this phenomenon observed to date all appear to involve smaller, more tightly bound binary star systems, rather than a chance encounter between two unrelated, independently orbiting stars like the Sun and a hypothetical visitor. A collision between a passing star and a planet, rather than the Sun itself, would in principle be an even more remote possibility, since a planet presents a target many hundreds of thousands of times smaller in cross-section than the Sun does. If such an encounter were somehow imagined regardless, it would resemble, on an enormously larger scale, the same physics that governs any high-speed collision between two bodies. The planet's material and the star's outer layers would interact violently, with an outcome dominated overwhelmingly by the star, given how completely its mass and energy would exceed the planet's own. The direct collision case sets the extreme far edge of a spectrum whose much more physically reasonable middle, an Oort cloud disturbance or an outer planet's orbit bent out of shape, is the more plausible physics at work. What remains is to ask, honestly and with real numbers where they exist, just how rare any part of this scenario, gentle or extreme, actually is. Astronomers can estimate how often close stellar encounters happen near the Sun by combining two things: the measured density of stars in the Sun's part of the galaxy, and the typical speeds at which those stars move relative to one another. From these figures, researchers have calculated rough encounter rates for different closeness thresholds. A star passing within roughly 1 light-year of the Sun, comparable to what Gliese 710 is expected to do, is estimated to happen, on average, perhaps a few times every million years, meaning it would have occurred perhaps a few thousand times across the Sun's full 4.6 billion year history. A number large enough that Scholz's star's real, confirmed close approach at Oort cloud distance is genuinely unsurprising in this light. A far closer pass, one bringing a star into the inner solar system among the planets, is estimated to be dramatically rarer, plausibly happening only a small handful of times, or perhaps not at all, across the entire history of the solar system so far, and current models predict nothing of the kind is likely within any humanly meaningful span of future time either. The reason for this steep drop in frequency, dropping so much faster than the distance itself decreases, comes back to simple geometry. The volume of space within 1 light-year of the Sun is enormously larger than the volume within, say, 100 astronomical units, meaning far more possible stellar paths intersect the larger, more distant zone than the small, close one. A useful way to hold this is that a close pass through the outer Oort cloud is like a stray shot landing somewhere within an entire city, while a pass through the planets themselves is like that same stray shot landing on one particular street corner. Both are possible. One is dramatically less likely than the other, for reasons of pure geometry rather than anything special about the solar system. This low overall rate also helps explain why the solar system's planets have kept their current, remarkably regular orbits for so long. If close stellar encounters capable of disturbing planetary orbits happened frequently, the solar system observed today, with 8 planets on stable, only mildly elliptical orbits, undisturbed for billions of years, would be a much less likely thing to find. Astronomers studying other star systems have in fact found some planetary systems with unusually tilted or eccentric orbits that may be evidence of past disruptive events, whether from a stellar encounter or from internal gravitational chaos among the system's own planets. The Sun's system, by contrast, looks like what a long, quiet, largely undisturbed 4.6 billion year history should look like, and the rarity estimates for close stellar encounters are consistent with exactly that outcome. Gaia and future missions like it continue to refine these estimates by finding and tracking more stars with greater precision, which means the list of known close approaches, both past and future, is likely to grow over time, even though the true underlying rate of dangerous planet-disturbing encounters is not expected to change. Astronomers are getting better at seeing the traffic that has always been there, not discovering that the traffic has become heavier. Every new candidate identified so far, including several found after Gliese 710, has followed the same broad pattern established by Gliese 710 and Shoal's star, a real, trackable close approach that nonetheless stays well clear of the planets. What all of this reframes, ultimately, is the entire thought experiment this account has followed. The physics of a close stellar pass, traced honestly from the Oort cloud inward to a hypothetical ejected planet and an all but impossible direct collision, is real physics, grounded in gravity, orbital mechanics, and mechanisms astronomers have observed elsewhere in the galaxy. But the astronomical rarity of the event itself is just as real and just as important to the final picture as the mechanism. The Sun formed about 4.6 billion years ago from a collapsing cloud of gas and dust, and in the time since, it has completed something on the order of 20 full orbits around the centre of the Milky Way, each one lasting roughly 230 million years, and carrying the entire solar system through a different region of the galactic disk, past countless other stars along the way. Across every one of those 20 circuits, through however many stellar neighbourhoods that path has taken it, the 8 planets have kept the same broad arrangement they hold today. Nearly circular orbits, all moving the same direction, all roughly in the same flattened plane. That continuity across such an enormous span of time and distance is itself strong evidence, alongside the probability and physics already traced, that close disruptive stellar encounters are rare enough that a solar system can complete 20 laps of a busy galaxy and never suffer one. Nothing in the real, tracked motion of Gliese 710, or in the real reconstructed history of Shoal's star, suggests the Sun is on any kind of collision course, gentle or otherwise, with anything in the foreseeable future. The physics traced here offers instead an honest look at what gravity would actually do if the odds ever did break the other way. A gravitational hand reaching into the loosely bound Oort cloud first, then on a genuinely close path, into the somewhat better anchored Kuiper belt, then into the tightly held realm of the planets themselves, where the same gravity that guides a spacecraft past Jupiter on a real mission could at a large enough scale guide an entire world out of the solar system forever. Tracing that chain also clarifies what actually protects a solar system, and it is not some special shield or unusual good fortune specific to the Sun. It is simply distance, repeated at every scale examined here. The distance between stars is so large that close encounters are rare. The distance between the outer Oort cloud and the inner planets is so large that even a real, confirmed close stellar pass like Shoal's stars affects almost nothing beyond the loosest, most distant material. The distance between a planet's orbit and true escape velocity is so large that only the most extreme, least probable encounters could ever close that gap. For all the stars the galaxy contains, space itself is overwhelmingly, almost incomprehensibly empty, and that emptiness is the single most important reason a system of worlds can last billions of years without being disturbed. The solar system is not permanently and completely safe from every gravitational disturbance for all remaining time. Researchers will keep refining exactly how often close stellar passes should be expected as missions like Gaia gather more data. But a star actually crossing through the solar system among the planets sits so far out on the improbable end of that physics that current evidence gives no reason to expect it at any identifiable point in the future, near or far. What the evidence does support confidently is the picture the Sun's own history already tells. 4.6 billion years, 20 galactic orbits, and 8 planets still exactly where gravity, undisturbed, always meant to keep them. None of this is scheduled. The one star whose path astronomers can actually trace with confidence, Gliese 710, comes nowhere near the planets. It grazes the outer edge of the Oort cloud in about 1.3 million years and leaves the Sun's 8 worlds exactly as it found them. The scenario traced here, a star crossing directly through the planets, asks what the same gravity would do if the odds ever broke the other way, and the honest answer is that it would do a great deal. Comets loosened by the trillion, orbits bent out of their calm ellipses, perhaps a planet cut loose from the Sun entirely, in the very worst and most improbable case a star and a star's debris colliding outright. What keeps that from being a live worry is not that the physics is gentle. It is that space itself is almost unimaginably empty, and stars that could do this kind of damage pass close enough to matter only a small handful of times across the entire multi-billion-year life of a solar system like ours. The Sun has completed roughly 20 full orbits of the galaxy since it formed, threading a crowded galactic disk without ever losing a planet to a passing star. That is not luck alone, it is what emptiness looks like when you have enough of it, and the same vast, quiet space that makes a stellar flyby rare is the reason a solar system can hold its shape for 4.6 billion years, and, so far, for every year since.